Well, I think we're about 2 minutes past the hour. So, hello everyone. Thank you for joining today's webinar. In this session, we will explore high performance building enclosure design with a focus on precast concrete wall assemblies and their role in meeting the evolving requirements of the National Energy Code of Canada for buildings. The webinar will be approximately 45 minutes in length, followed by we'll allow about 10 to 15 minutes at the end for Q&A. John might also decide during the presentation to answer certain questions. Participants are muted from the discussion, but you're welcome to ask any questions by typing them in the Q&A box. And you should be able to locate it at the bottom of your screen. You can also ask questions on the chat, but I think for keeping track and answering them in order as received might be easier to type your questions on the Q&A box. The recording of the session will be available on CPCI's Learn on Demand site afterwards, and the link will be shared with everyone. We will also share the presentation slides in the chat if you want to download and follow along. In addition, attendees who participate in the full session will receive a certificate to qualify for professional development hours. Today's webinar will be presented by Dr. John Straube, Principal at RDH Building Science. John conducts forensic investigations, assists with the design of new high-performance buildings, and leads research projects in the areas of low-energy building design, building enclosure performance, and field performance monitoring. Dr. Straube is also a faculty member in the School of Architecture and the Department of Civil and Environmental Engineering at the University of Waterloo. He's the author and a co-author of over 100 published technical papers. Without further ado, let's begin the presentation. Over to you, John.
Thank you. Been doing a number of presentations over the years on precast concrete enclosures because I come at this from the enclosure world, not from, say, structural engineering or prefabrication. Really, I come from the enclosure world of how you design good enclosures. But I also will say that as I was reviewing what I'm presenting today, a bunch of the advice that I'm going to provide or recommendations are also come from my forensic experience of looking at and solving problems. And so good engineering involves avoiding a problem while you design the product, as opposed to solving it afterwards. So I'm going to try and take advantage of our experience. So I'm going to start with a high-level review of precast systems, make sure we're using the same words on the same page, and then look at briefly some details for high performance and point towards other resources. And then, to keep the title honest, we're going to look at some innovations, things that are happening in the industry that are improvements, changes, et cetera. And then take a chunk of the end of the presentation to look at, in particular, the National Energy Code for Building in its newest version, but also similar requirements are in ASHRAE 90.1 2022, which is a common energy code in the United States and was once common in Canada. And all of them are focusing on thermal bridging and solving thermal bridging, and therefore how that addresses the precast concrete enclosure will be discussed. So again, as in my normal approach of making sure that we're using the same words to mean the same things, what do I mean by high performance enclosures? Well, I mean high levels of control, which means in different projects, you might focus on say heat, energy performance, or you might deal with air tightness might be a critical requirement, or you may be very concerned about rain penetration, fire or sound. And whatever that is, it's usually some mix of all of those. And so high performance enclosure is one that performs well in many or all of these control requirements. And many times people think that the reason that we have poor performance is because of a bad choice of a material or a layer. They blame it on a membrane, or they blame it on the concrete or a steel sheet. But really, it's almost always poor continuity that limits our performance. And by that, I mean, if we're talking heat, a lack of insulation continuity provides a short circuit or thermal bridge for heat flow. Poor continuity means we have a hole in our air barrier, and so air leaks in or out. Poor continuity means our water resistive layer is not well detailed and it has a hole in it and it causes leaks. So that's why continuity is actually far more important than just specifying the layers. So those types of problems are solved by having great continuity, and that could be simply summarized as no holes. Remember, the saying goes, the only building that should be holy is a church. But we're trying to make sure that we have no holes for heat, air, water, fire, sound. And when we want to get high performance, we're trying to avoid those holes and then have good control layers, good layers of insulation, strong and airtight air barriers, etc. So, and high performance is a thing that a label that has emerged in the last decade or so, be driven by sort of the changing demands of building codes, which are asking us now to provide air barriers, to have better thermal bridge-free design. We're even asking for carbon saving or measured energy performance, the ability to survive power outages, wildfires, ice storms, and that kind of thing. And just simply owners saying the buildings I'm previously getting are not as good as I'd like them to be in terms of comfort, in terms of durability, in terms of operating cost. And so all of those things can mean high performance, and every project should actually address at the beginning stages which aspects of these performance are we looking for. So to start with, I want to just remind everybody that there is this best practice guide, been out there for quite a few, 5, 6, 7 years even, and it's got many practical and effective details. It tries to lay out the principles of good precast concrete enclosure design, and also to consider things about continuous insulation, and good rainwater penetration control, etc. So you can just download that from the web at cpci.ca. So two common types of building enclosures. One, a conventional panel or single withe panel or architectural precast is sort of the labels applied to this. So there's a single layer of concrete, and then we put the rest of the enclosure layers that are needed, add that in on the job site. Integrally insulated panels, or more commonly known as sandwich panels, two layers of concrete which sandwich around a layer of a continuous insulation. So conventional panels here, I'm showing you just a smorgasbord of different systems and what they can look like. And although many of us may think of buildings like the Federal Reserve or the FBI headquarters in Buffalo with rectangular windows and simple facades, you can get quite elaborate with those facades if you design it from the beginning. And we often are mixing and matching, as shown in the upper right, different systems. So there's precast over some of these floors, and there's curtain wall and storefront over other parts of the enclosure wall. Now, I'm sure CPCI wants you to use only precast, but I'm going to tell you that there's actually lots of reasons why we might mix and match systems to meet certain program or aesthetics. So if we think about what is architectural precast, single withe panels, it's prefabricated cladding, but it's more than cladding because it also is the structural component that takes the wind loads and the gravity loads and transfers them back to the superstructure. We do have to do the insulation and finish on the job site, and that's been the traditional way. But lately we're seeing, and one of the innovations is that we're putting the windows and doors in the panel in the factory. And so I'll show you some pictures of that. And one of the reasons people use architectural precast is that, well, a single layer of concrete is going to save weight and save money versus two layers. But we'll look at why actually sandwich panels are becoming relatively more common because they solve more problems that are modern. So here's a pretty busy diagram because we're trying to cram all kinds of good building science and experience into this one detail. which is now looking here at the floor slab. And couple things to note. The yellow line there is saying it's a continuous layer of insulation. And that insulation can be spray foam, it could be board foam with the joints taped, it can be now faced stone wool with taped joints. Um, and that is necessary to stop air from getting to the cold precast. But the precast concrete itself is performing as the air barrier. You can't really come up with a stronger, a stiffer, a more reliable air barrier than, say, 4 to 8 inches of concrete, reinforced concrete. That's a pretty amazing air barrier. So, with respect to rainwater control, and we'll talk about it a bit more. It's showing a two-stage joint, meaning we're relying on the concrete to stop water penetration because concrete does that. Um, and we're using 2 layers of sealant at the joints so that we can use a rain screen approach whereby we accept the outer layer may have failures and penetrations, but we're draining behind that layer. And we're using an inner layer to be more the air and water barrier as we would in a rain screen system. There's a couple of other details here about fire stopping to think about, where to put your columns in early stage design to allow easy installation. And we can get, typically these are like R10-ish, and we are often now delivering these systems in the R20-ish range, real life. So I'm going to now move just to show you some pictures, and I see the point about a pointer, but I will maybe use the pointer where it's not clear elsewhere. This is an example of a building in New York City, and I showed you some pictures of architectural precast, but yeah, I don't know why the screen is not changing. So here you can see some pictures of a project where that architectural precast is actually using embedded steel and clay brick to provide a very different range of finishes, one that happens to fit into this neighborhood. Another thing about this project that's interesting and worthy of note is that the windows are pre-installed, lifting off the truck. They have the windows in them. And what that means is that the building is quote unquote closed in as soon as the panel is set. And when I'm putting quotes around that, it means that you still have to seal the joints. And that's going to come up as I talk about joints, 2 and 3 layer joints. Now, another thing to keep in mind is that although it is most economical to use only one size of large panel and keep it flat, for important projects that you have the budget, you can make panels that are not flat. And there's a lot of remarkable things that can be done today. One of my kind of favorite buildings is 11 Hoyt Street in New York City, where they've managed to have repeating panels, but by having curves in them, and presetting the windows in the factory, literally 1,000, I don't know, it must be close to be 1,000 kilometers away, 700 kilometers away where they made it. It really works. So sandwich panel here. What do they look like? Well, as we switch to sandwich panels, we have 2 layers of concrete with a sandwich of insulation. Not a tasty sandwich, just saying it's a sandwich. And the photograph here is of a load-bearing sandwich panel. So it became part of a total precast system where the 8-inch inside concrete can support very many stories, dozens of stories. So it's also showing that we have about a 4-inch of insulation. So the advantage of a sandwich panel, of course, is that it's a fully prefabricated enclosure system. You don't have to do anything more to the interior. It's already got fire protection. But of course, in almost all cases, we're at a very minimum painting the inside, but usually adding steel studs and gypsum wall board to provide wiring for both power and communication security, et cetera. And if you install the sandwich panel and have windows installed in the factory, it means that you're literally put one layer of sealant at the joints, and you can turn the heating on, and it doesn't matter what the weather is outside. And that can be a very important factor in terms of getting schedules of larger and multi-story buildings so that you're not affected by the winter conditions that occasionally strike some parts of our countries. So here's the detail of the architectural the sandwich panel, like the architectural precast panel. And I was just going to use this laser pointer here to identify. We have the two-stage joint. We have, in this case, the anchor, the steel anchor that transfers the gravity loads and the wind loads to the superstructure is entirely inside of the insulation, air, and water barrier. So it's very protected and durable. It doesn't have any impact on thermal performance because your continuous yellow insulation is a continuous R value. So you do have to worry a bit about fire stopping. Like a curtain wall system, it flies past the floor. You have to think about smoke seals and fire stops. But this is showing a lot of details about how you get to a high performance system. And how you increase the R value of this system to meet more demanding codes is pretty simple. You make the insulation layer thicker. Um, and so that is really what happens here, is that you make the insulation layer thicker, you get more R value. I'm going to show you some images of how they connect the outer layer and the inner layer of concrete in a thermally effective and structural way at the end of the seminar. So here's an example of some sandwich panels being constructed with the windows installed. Happens to show a different sort of exterior finish. You can see how the lintels are shown in a different color of concrete than the stone details. And you can see it's a 4 inches of continuous insulation. This is a pretty high performance project in Ontario. And now you lift this into place and all that work is done. So as I mentioned, you can use sandwich panels as part of the load-bearing structure of the building. The shear walls and the exterior walls can be load-bearing so that you don't actually have to build up a structural frame. You can use the precast itself. In this case, this is in Alberta, a northern Alberta project. The windows are installed, and of course, pretty much any window system can be used in these precast systems. They could be fiberglass, vinyl, aluminum, and there is a fair bit of design work in any kind of system to be able to figure out how the windows integrate with the air and water tightness of the wall that they're inserted in. And that's no different for prefab precast systems. And you can see there's a couple of different finishes here. This is the finished project. In this case, they had 4 inches of extruded insulation to give them about an R20, but we have other options and it can adjust. You'll also notice that the balconies here are separate and precast, and usually in modern practice, those precast balconies would be clipped onto the building to avoid penetrating through the insulation and the air tightness and the water control. So that maybe leads to one of the most, I don't know, common types of questions about modern precast. Of course, there's a lot of interest in precast because there's a desire to do more prefabricated or off-site construction. And precast systems have sort of the longest continuous track record of prefabricated panels of any other system. However, as the industry has gotten smarter about the importance of rain penetration resistance, we start thinking more about how do we apply this to precast. And as early as 1973, the Precast Concrete Institute in the United States released a report with drawings of the solution. You use two-stage joints between the panels, and you use the concrete as the water-resistant layer. I also want to point out that that's exactly the approach we use for curtain walls. Nobody suggests that we need to drain the space between the sheets of glass in an IGU, insulated glazing unit, but everybody accepts that we need to drain the joints between between curtain wall elements and the glass elements. And the same philosophical approach has been used for a long time to provide a rain screen at the joint and a perfect barrier at the concrete. And so, and I guess I'll show you some joints in a moment to maybe elaborate on some of the questions. Um, but one of the things that seems to be under-recognized is that we've been building undrained precast for almost the entire history of precast. And we've learned where and how they leak, and they tend to leak at joints and penetrations, not through the panel. But as people have tried to provide drainage in especially single wides precast, we've learned that there are some serious risks and disadvantages. One of them, of course, is that the anchors are now exposed to the rainwater that might be draining down the back of the precast. And so that puts a lot more pressure on the durability of that anchor. But also, it results in a risk that now I have a penetration through the water control layer in the form of that structural anchor that I now have to detail. We can do it. It's just complex and expensive and a little bit risky. And so there are serious constructability issues. And also, we give up the ability to use the concrete as the air and watertight layer, even though it's exceptional and way better than any membrane you can buy in terms of air and water tightness. So we do know how to drain sandwich panels. It's relatively easy. Again, it's not been done a lot simply because they don't have there's no need for it. It's only driven by external forces that like insurance companies who don't understand. So let's go look here at some of the joints, which are the core of the rain penetration and air tightness of a precast system. Uh, Two-stage joint means there's an outer layer, which is supposed to be pretty tight, but we accept could fail because it's exposed to the sun. And it has drainage holes in it that lets the water out. And then we have a secondary seal on the inside, which is intended to be continuous and is drained out at intermittent locations through weep holes. Very practically in precast, you just leave an opening in the sealant and you curve over that outer layer of sealant on a pushed in backer rod so that you can nicely shape the drain opening. There are historically the way we did this many years ago, and I will say when I first entered the industry, the left-hand image was what we were working with. I was wet behind my ears, had no idea, and they were starting to realize the limitations of that detail. And that primary problem was that inner seal, which in the two-stage joint design is the air and water barrier, was difficult to make continuous because it was applied from the inside. And when you apply it from the inside, you have these things called floor slabs in the way. And then you get even worse perimeter beams, columns, drop panels, and even I've seen problems around drain lines and so on, where you just can't get a continuous bead of sealant from the inside. And so that's why we moved more recently to the right-hand side. And that's what I was saying. Like when I entered the industry, we started to be moving to the right-hand side detail, where you had the inner sealant was applied from the outside. And that created some significant benefits because you could easily make it continuous now. It was easy to drain it to the outside and so on. However, over time, as the insulation layer got thicker, it became more and more practically challenging to reach all the way back to do the sealant and to do quality control on the sealant. So as we now enter a world where there's lots of insulation in sandwich panels in particular, the movement has been in the last at least 5 years, and I'm seeing almost universally in my region, even in single wide precast, two layers of sealant separated by a gap, drain the gap to the outside, and it's easy to install and easy to inspect. Now, that brings up the issue of the triple stage joint. Um, and why do we do, I don't even call it, I shouldn't call it triple stage. It's still a two-stage joint with a third seal on the inside. And that third seal is like that's shown right here. It's could be an option, and people, especially builders, are recommending it because it accelerates the close in of the building. Remember how I mentioned that when you put the panel up, if the windows are installed, you've kept the rain and the wind out, except at the joints. If you're working on a multi-story building, it can take some time before you can actually hang a swing stage and do sealant at those joints. So to make that panel air and water tight, you want to add a layer of sealant fairly early in the construction cycle. And that's what's found to be relatively easy and inexpensive from the inside. So you actually apply this inside seal here first during construction, and you can decide to use a pretty low quality sealant because it's just got to last most of the construction cycle. Then when the building is topped out, you drop the swing stage and you install these two stages of sealants. And I mentioned quality control. It's really inexpensive to inject water into that gap using a syringe or a hypodermic needle or something like that to inject water, make sure the water comes out of the appropriate weep hole. And you can do that many times really inexpensively. And it's a completely definitive test that they have a drained joint. On the right-hand side of this image, I'm showing an example which has come up for some higher performing buildings. Museums, swimming pools, and some passive house projects have been worried about insulation being interrupted at the joint. Now, while air is not a bad insulator, we have ways of filling these joints up either with some sort of expanding foam, pre-compressed foam gaskets, or even we've seen people insert backer rods into this joint because that foam is insulation. And we've done the thermal modeling to demonstrate that it actually can perform quite well. So that's why we have this triple seal. You should not rely on this in any way to keep the rainwater out, but it is very effective during original construction. So in somebody asked a question about flame spread and or fire protection. And generally speaking, if I look at a detail like this, it depends on how which particular code clause you're worrying about, whether it's when you're using non-combustible cladding like brick over CMU, there's different rules, and it's a similar set of rules that apply to precast concrete over precast concrete, which is a sandwich panel. And so you don't have to do the full NFPA 285 or S134 test when we're using these non-combustible components with combustible insulation. However, that said, there are situations where you're looking for either a different building code or different fire requirements. And so there's a number of options, such as using just a perimeter of non-combustible insulation. That's not that uncommonly done in some jurisdictions, but it's a kind of a rare problem, and it's not usually a problem. I would also like to, before I move on to talking about thermal bridging and so on, is to say, recognize that we have to do inspection on our building enclosures, and they may require maintenance. Now, many systems don't actually tell you how to do this. And it's interesting that, look, precast concrete is a low maintenance requirement, but it's not zero. Every window system needs to be inspected, and you have to check that the gaskets and seals may need to be updated. I mean, they don't last much more than 20, 30 years. And so similarly, so this is a manual about how do you go about inspecting it? How do you set up cycles so that you can have a building enclosure that can last well, a century if you'd like it to. Of course, you're going to have to change the windows. So this lets us jump into the discussion of new energy codes. And in some ways, I think we're going to see some innovation in the responses to how do we respond to these demanding energy codes in a way that's economical and effective. And is pretty obvious to everybody who's involved in the industry that we have a increasingly challenging code environment. Now, I've only got this chart up to the 2015 code or the 2013 90.1. It takes some effort to run 100 simulations, but we are definitely trying hard to reduce the energy demand over buildings that were built previously. And one of the most important things that's coming out of the new codes is that you need to address thermal bridging. And it turns out that thermal bridging can make a meaningful difference to the energy flow. When you start recognizing how significant thermal bridging is in normal systems, you start realizing how big of a difference there is between different types of designs. So originally, we did this project many years ago when we looked at the NECB 2015. We produced a guide which is still available. And at that time in Canada, there were 3 different energy codes in force. But now most jurisdictions in Canada are moving to NECB 2020 and 25. In the United States, there still is a wide range of codes that apply. And so there's many jurisdictions you don't have to consider thermal bridging in much detail, but there are many jurisdictions where they are using stretch codes or setting higher standards, whether it's municipal wide or statewide, where you in fact do need to use the new ASHRAE 90.1 standard, which requires you to consider thermal bridging. And so that's why there's a new guide, which is based on the 2025 NECB thermal code. And the intention is, again, like the last one, to give early stage design assistance so that owners, builders, architects can say, roughly how thick do I have to make the insulation and what kind of details do I have to consider to meet the code, the energy code. And you want to do that relatively early so that you have a realistic assessment of how thick your enclosure is going to be and what kind of details you need to consider, because it's as much about the details as it is about how thick the insulation is. And so the early stage planning can alert you to these are the kind of details you need to deliver, and this is the kind of thickness of insulation you need to think about. So the changes between 2017, 2025 has been increasing R value requirements, decreasing U values, more focus on thermal bridging at all kinds of penetrations, and we're going to look at that. And also, there's this concept of energy tiers, similar to the stretch code in the United States, where you have a code minimum, but you might get some bonuses if you go to a higher performance level. And so that's a different tier of energy saving that's available in the NECB. The image on the bottom right is just a reminder that's the energy consumption for average Canadian office buildings when they've done a survey of all office buildings. And well over half of the energy consumption in office buildings in Canada is space heating. And that I show that because sometimes I get the comment that, hey, do I really care about heat energy in an office building? Isn't it cooling dominated? And the short answer is, well, no, if you mean cooling dominated is most energy. Cooling is actually a relatively modest annual energy consumption. So these are just an example of the energy tiers. The minimum is tier 1. That's the normal approach. And then as you go to tier 2, 3, and 4, you reduce energy 25% per step. So if you're trying to get to net zero or some sort of very low carbon building, you might be looking at tier 3 or even tier 4. Now, first thing to say is that when we're dealing with the thermal performance of any enclosure system, and precast is no different, is that there isn't a single R value anymore. It depends. And I know people are probably sick of hearing it depends from consultants, but it really does depend on your pathway that you go. And you have always the option to try and do a full energy model and show that your combination of lighting and HVAC and enclosure results in energy consumption that's low enough to meet the intent of the code. But there's a lot of times when we're going to use a simple trade-off approach where you can switch between window R value and wall R value, or window area and wall area. That's actually quite a powerful performance path for buildings like warehouses and such, where you can reduce the window area and that saves so much energy that it really reduces the demands on the insulation of the opaque wall. And then there's a prescriptive path, and the prescriptive path just says this is what you have to do. Just in case someone isn't aware of the climate zones in Canada, here they are. They are literally the same as the ASHRAE climate zones used in the United States. So we have between zones 4 and zones 8 in Canada. And as you get higher, it gets colder. This is a 2025 R value table. So you have to flip the U value around so that you can convert their numbers to R values. And I'm using R values because most of us think that way. And just to be clear, the R values are, as you can see, for walls in the 20-ish land for zone 4 and 5, and in the 24 area for zone 6 and 7A. And then when you get to zone 7B, which is starting to be much north of Edmonton or into Yellowknife, you're going into zone 8, only there do we see the R values get to R30 and even 35. But what's important to remember about these R values is that these are real R values. They are R values that include thermal bridging. And that can be quite significant for some systems. And therefore, getting to these R values is easy for just the wall. It's hard if you include thermal bridging. So most of us were taught or learned on the job that the way you figure out the R value of your enclosure is you write down the R value of each of the layers and then you add them all up. The reason we like R value is you can simply add R's. And then you invert that total number to get the U value and compare to the code mandated values for U values and make sure that you're compliant. Now, the problem with this simple drawing is that, of course, it's a two-dimensional drawing or a one-dimensional drawing, really. It's just layers, and it doesn't include any of the things that could cause thermal bridging. So in terms of how do we calculate this? Well, a simple system like made of 3 layers, we know the RSI value for each layer or the R value. You add it up, you get a number for total RSI, total R, then you invert it and you get a U value. So in the building codes now, we include the R value of all of the layers, the air films, the drywall, the insulation, air spaces, etc. However, be clear, the insulation is going to provide the vast majority of this. So when we're doing calculations at early stage, we'll often just sort of not include the drywall or the air films, or we'll just include an allowance of R1 or R2 for the air gap and the air films. Because most of the time to meet these codes, we're talking about it's the insulation, and that's what we have to achieve. So let's look at thermal bridging and how that would affect these values. Thermal bridging is just a word we use to say where heat flows more quickly through the enclosure than the average of the enclosure or the majority of the enclosure. And they bridge around the insulation is where the term originally came from. It is quite plausible in practical building systems for thermal bridging to reduce the effective R value by more than 50%. As an example, if you were to have a concrete wall sitting on a concrete slab, even without balconies, you will have heat flow through the slab into the concrete wall. If the insulation's on the inside, as shown on this drawing, just that detail will reduce the R value by 50%. Adding a balcony will reduce it further. And of course, windows will reduce it even further. And therefore, if the insulation layer in this image on the right-hand side here were to be, say, R20, the effective R value of a typical building with balconies and windows will be in the order of 6, maybe 7. And so that's a very significant reduction. That is why policymakers have said we have to start including thermal bridging in our building codes. So just take a look at this sort of concrete with a rigid board, a fibrous insulation between steel studs and drywall. We, in the past, would just talk about the R value of the insulation that we were installing. That would be the R value of just, say, R10 for that rigid foam layer, R20 for the fiberglass batt layer. And however, then we would start saying, oh, let's get sophisticated and add the layers of concrete and drywall. Well, then we'd add like R2 or something like that for air films and drywall. And then we would get to the first step of what is a more realistic R value. And this is termed the clear wall R value. And the clear wall R value is including the thermal bridging, the two-dimensional thermal bridging of repeating elements. And what that generally means is those Z-girts or Z-girts that are shown holding up the insulation, the rigid board, and the C-shaped steel studs. Those are, they occur every 16 or 24 inches. You need to include that in the clear wall R value. That's been something that's been mostly handled in the codes up until now. And it has a big impact on those light gauge steel framing elements and have driven us to having more exterior continuous insulation. Now, but it's more than just those continuous ones, because if I look at a real wall system that might have a concrete slab at the bottom here, it might have a steel beam at the top. When we have a precast, in this case, single wide connection, there is the floor slab that's penetrating through some of the insulation. We have the steel studs, of course, as like before, but we also have to add the beam and the effect of the parapet, potentially providing a shortcut. And that is called the whole wall R value, where we include these things like balconies, parapets, edges of windows, slab edges, etc. That's where the codes are moving to. So as an example, the language in the National Energy Code for buildings in Canada is really quite succinct in clause 3117, where it says to meet the requirements of R value or U value, you shall include the effect of thermal bridging, which includes point thermal bridges, linear thermal bridges, and thermal bridges at junctions between building envelope material components and assemblies. Now, in a way, that's short, but it doesn't tell you what do we mean by point thermal bridges and linear thermal bridges, which is why I'm going to show you what the note says. But the note is telling you that by point thermal bridges, we're talking about things like precast anchors that connect the concrete back to the superstructure. Brick ties would be cladding connection clips because these are points. And linear thermal bridges are, as shown here, a floor slab that cuts through insulation or a continuous Z-girt or equivalent shelf angles. So here they list linear elements to be studs, joists, ancillary members, lintels, plates, flashings, you name it, it's included. And I think that's the point, is that we're supposed to be including all these things and including junctions between windows and canopies, slab edges, and so on. So pretty much everything. So the guide from CPCI that's available will be giving you guidance on how to include these types of thermal bridging at early stage design without doing ridiculous amounts of calculations. So as an example, this is a table of the effective R value for a layer that's made up of light gauge steel framing, and it's got gypsum board on the inside. And so you can see that if you have a 3.5-inch steel stud with an R15 rated bat, you'll end up with about R7.8 is what the effective R value is. And you can do the same and see that you can interpolate if you had R14 and come up with an estimate. Now, how would we actually use that? Well, when we start with a clear wall before we calculate the effect of these other thermal bridges. We start with a clear wall, and this is one of the examples in the guide that says, okay, let's look at a panel, single wide panel, 5 inches of concrete, 3 inches of closed cell spray polyurethane foam, steel stud that's got bad insulation in it. And when you just add up simple numbers that are provided by tables, you get around R20.5 with an empty stud and R25.7 with an R13 bat. And that's sounds like a pretty good wall, but actually it has a hard time meeting zone 6 when we include some of the thermal bridges that we'll talk about. So one of the obvious thermal bridges that we add to this is the floor slab. And so there are tables of information that explains how we would calculate the effect of a floor slab. You can put in various thicknesses of floor slab, but a critical dimension, which may not be obvious, is how big that fire stopping insulation is. It was typically been like inch to inch and a half just for dimensional tolerances, but there's a strong thermal reason to increase that to 2, 3, even 4 inches. And so the precast manufacturer has to modify their connections. And so if you can see that R22.9, it was 25.7 if you look right here. And now it goes to 22.9, including the floor. However, if I put 4 inches of fire stopping, I'm 24.9. And that's the difference between meeting zone 6 and not meeting zone 6 prescriptively. Now, the thermal bridging envelope bridging guide, which you sponsored by British Columbia Hydro, widely available. It's referenced in the NECB. It's referenced in ASHRAE 90.1, and there's a lot of useful information in there. So they too have a clear wall value for some precast systems, and more usefully, they also give you some way of assessing the perimeter details for things like windows. And parapets in the upper right here. So when you start including the window details, and you'll want to be looking at guides like this to get more information. One thing that's missing from the guide is the impact of normal precast anchors. This is, of course, only important for single wide precasts. Sandwich panels don't have the challenge. And we've done some three-dimensional computer models and presented the results in the guide. And it turns out that in most cases, they don't have a huge impact, but it's definitely something you may want to show your authority having jurisdiction to say that you have considered the kind of anchor I'm showing on the right-hand side there, and gives you a way of calculating the impact on the panel depending on thickness of the stone wool fire stopping. And then you can say per anchor how much heat loss, and use that to adjust. So that's in the guide right now. Another final point to mention before we wrap it up is that the thermal bridge of the interwithe connectors is supposed to be included. It's explicitly called out that these types of ties. Now, there's a lot of different types of inner wide connectors or sandwich panel connectors on the marketplace. I'm showing some images here. And you just need a chi factor like we've created for some of the anchors. We need that for these types of interwide connectors. And CPCI is sponsoring a project where they're going to be delivering a bunch of these numbers so that they're not, again, they don't have a big impact on the thermal performance, but people want the proof. They want to know, and they want to see the difference between using a steel connector and a fiber reinforced plastic one. And so that work is definitely underway. So I think I just see a question there from Joel I'll talk about in a moment, but precast panels, just summary wise, have a long record of prefabricated construction. People seem to forget that we have prefabricated systems that we've been using for a long time. We've been building apartment buildings, multi-story apartment buildings by the hundreds starting in the 1920s. I know of projects. But what we've changed over the years is, of course, two-stage drain joints in the last 30 years as a way of solving rainwater leakage. We're only recently in the last decade starting to see more and more windows being installed in the panels in the factory that to solve problems on the job site and accelerate construction. And now we're seeing more concern with thermal bridge reductions. It's not enough just to put some insulation in the panel. It's also dealing with the thermal bridge, and the code is driving that. So take advantage of the guides and resources that we have that are on CPCI's website. And but I also would say that let me just try and ask some questions. Can you talk about the requirements for a vapor barrier on the interior of walls in a single wide configuration? You need a vapor, I'm not going to call it a barrier, you need a vapor control layer of some form on the inside of your insulation in single wide precast in zone 5 and up. And that includes Ithaca, New York. But that doesn't have to necessarily be a membrane you buy, right? It could be the insulation you use, like spray foam. Or it doesn't have to be a sheet of poly. You could get stone wool with an integrated smart vapor barrier, smart vapor control layer. It's not a vapor barrier, which opens up to let drying to the inside in the summertime and closes to stop in the wintertime. But if you're using vapor permeable insulation, you will need some vapor control layer. That's for sure. And again, I think there was a smart vapor, thermal bowing. Thermal bowing is kind of predictable. We're not precise, but we can certainly assess it. Basically, if you have a large temperature gradient across a panel, the outside, let's say, is hot, it expands, and the inside doesn't, you will end up with bowing. When it comes to sandwich panels, that's dealt with by not making the outer and inner wide act perfectly together. There's only some sharing of the load to manage thermal bowing. In single wide precast, it's not really a problem because the temperature gradient across the concrete is almost zero. So it's more of a thing, thermal bowing for sandwich panels, and it's manageable by design. Although I think it's worth raising the issue whenever you have deep panels that span long distances to make sure the producer understands your concerns. Oh yeah, Joel. Yeah, Ronnie mentions to Joel's response is make sure the insulation is tight to that gap. You should have no gap between the concrete and the insulation, no matter what. So I'm just checking back to see if there were any. I mean, other than the whole fire stopping details, which again had like you could ask John how I don't know why how we built the last 500 foam paneled precast concrete, like 500 of them in the last 5 years in a few hundred miles of my home, and somehow we've managed to make that happen. So the fire stop detail, I don't know what's special about your project that requires it. But so it's not probably a general thing that we can answer on this type of a format. So any other questions, or Val, do you have any sort of, we did go out a little bit. Any air tightness
Yeah.
considerations? One thing, Noah, to realize again, we have on the CPCI website a pretty detailed air tightness testing report. And I for one, thought we didn't need to do that because it was obvious to me that 4 inches of precast concrete is incredibly airtight and strong.
Mm.
But people need to have a report with an ASTM number, and that is available to you on the CPCI website. It's an air tightness test, and so you definitely need air tightness, but you need a continuous line of sealant on the inside, continuous concrete, and you can have fantastic air tightness. It's
That's
all
great.
details. Go
That's
ahead.
great, John. I think we're a couple of minutes past the hour, but I think there were just a few more questions if we can. I was trying to kind of keep track of quite a few questions were submitted. A lot of them were addressed as you were going through your presentation, but there was one in a face seal sandwich wall panels installed in cold climates. Are we seeing any buildup of moisture from vapor drive between the panels when older assemblies are retrofit with coatings to address any water entry from the panels?
Okay, so first of all, if you're talking about the panel being face sealed, yes, the outer concrete is the designed water control layer. Are we seeing any moisture between the foam, or typically it's foam insulation, and the concrete? Never heard of it, never seen it. Maybe someone has. It seems very unlikely. You'd have to have a problem because both the concrete and the foam insulation have some vapor permeance. So if you somehow get water in there, like you do when you build it, it does dry out. It just takes a while. So it can't allow a lot of water
Mm.
in, but I don't see how any water gets in service without having a visible crack. And if you have a visible crack, that's a defect that needs to be fixed.
Mm. Great. One quick, I think you might have touched a little bit on it already, but it has to do with the combustibility of the insulation, that it's encapsulated between the two concrete layers. How do you protect typically the insulation for flame spread in compliance with the S134 for cladding systems?
Yeah, I did try and address that, Val, and the
Yeah.
short answer is that we don't, because it's a non-combustible inner wide, non-combustible outer wide, and so except for, there can be situations where it might come up, but generally it's not.
Mhm.
That doesn't mean that there might not be a way. And if there is a concern, and this type sometimes shows up, I know in Vancouver, for example, they will put when they pour the panels, the sandwich panels, they'll put 6 inches of stone wool around the perimeter to make a fire resistant perimeter and allowing the foam to be the rest of the panel. But it's just not, it doesn't come up very often. It's like 95+% of the thousands of buildings that are built this way
Yeah.
do not have to, and the S134, it doesn't really apply for this system.
Yep. Does the CSA A44.4 440.4 still apply for Windows installation in precast?
I would say yes. I can't tell you that I've read whether they exclude it or include it, but we definitely spend all kinds of time with A440. I would say 0.6.
Mm-hmm.
That would be what we would recommend is the high exposure for most of these projects. And that's what I would be using as a guideline for how do I make sure the windows are installed in a durable and effective way.
Great. Let's see. Maybe if we can ask another question. Do you have any? I think you addressed that already, but do you see any issues with using two-stage joints on a single white wall system, but using rock wool and a 6 mm poly on the inside? The insulation
Yeah.
is continuous and no air gap.
So that design detail is good, except I'm a bit hesitant about the 6 mil poly because it's quite difficult to actually attach that 6 mil poly in a durable way that it doesn't floff off or leave the chat.
Mm.
And so that's why. But there's now a stone wool product that has a fully adhered smart vapor retarder. So it actually comes almost like it's like a board with an airtight on the inside that also controls vapor. I would always prefer that. You install that, tape the joints, then you're good. And that's an
Yep.
excellent way to deal with what is a real fire issue, is that sometimes the fire on the inside, you need to provide fire protection to the insulation on single wide precast.
All right. Well, with that, I think we're already 7 minutes past the hour. But if there are any questions, and there might be a few that we'll go back and I'll make sure to follow up with the fellows that submitted those questions. Um,
And
did you have
also the
anything else?
certificate of
Yeah.
attendance, Val. I mean,
Mhm.
I can't answer that question, but I'm assuming, yeah, okay, all right. We have an answer ready. They're going to be sent. That's good.
Okay, perfect. All right, so with that, we will conclude the Q&A session and the presentation for today. Thank you again for taking the time to join us, and thank you to our presenter, John Straube. As mentioned earlier, the video presentation of today's webinar will be posted on our platform on Learn on Demand and will be sent to all attendees along with your certificates of completion. If you have any additional questions, please reach out to CPCI at info@cpci.ca. Thank you and have a great afternoon, everyone. Thank you, John.
Cheers, all.